Okay, so if we have a one-dimensional reservoir, a good approximation to a one-dimensional reservoir could be, not a reservoir, but a one-dimensional porous media would be like a core that you might use in the lab to do core floods on and test for material properties. Okay, so this is a one-dimensional porous media, so it has some mass flowing in and some mass flowing out. Right? And what we're going to do, we're going to take a little bitty sliver of it, a little differential sliver, and we're going to pull that out, and we're going to write a mass balance on this little sliver. Right? So this little sliver it has a differential thickness dx. All right? And we're going to write the mass balance not on the porous media itself, but rather on the fluid flowing through the porous media. Right? So the fluid has a density. The porous media has a porosity, right? And that's going to help us determine how much volume of fluid is flowing through it. And since it's one-dimensional, we're going to assume it has a cross-sectional area. Right? And so I think in words and probably in Reservoir 2, Dr. Lake is sort of kind of famous for, not famous, but he is famous, but not for this necessarily. But his saying is that mass balance is mass in, right, minus mass out, plus any generation or consumption has to equal the accumulation. Right, so you've probably seen or heard that before, okay? And so mass in and mass out is sort of easy to understand. If we're going to take some little reference volume and if we measured how much went in and how much went out. But what about generation? Where would generation come from? Like what's an example? Say if we're looking at if our control volume, our little small element, is the size of this room in a reservoir, and it just happens to be the exact point where a well comes into our. Right, so the well itself could be a source of generation if we're injecting water, right, or consumption if we're producing, right. So in the size of a reservoir, we don't really consider the volume of the well itself. We just sort of think of it like a little point or line source or sink. Right? So we don't really consider the volume of the well bore. Rather, it's an infinitesimally small thing in our reservoir that is either going to produce or inject mass. Okay, and so that's where generation and consumption comes from. And then accumulation we would get from because the fluid and the rock is compressible, right? So that's where any accumulation would come from. So the thing that I'm going to do, just a tiny bit different than the notes, is that if I divide both sides of this equation by some increment of time, then, and I can do that, right? I can manipulate any equation. As long as I multiply or divide by the same quantity everywhere, then I can do that, right? I don't change the equation. So this equation is still valid, but in words, this sort of changes what I'm saying. Now, if I divide by time or an increment of time, now I'm talking about a rate, right? So we have the first term is like the rate of mass in minus the rate of mass out plus the rate of generation equals the rate of accumulation. Right? So just a subtle change in the wording then sort of makes, in my opinion, the derivation a little bit more straightforward. So if we go back up to our differential volume, where we're going to write the mass balance, we have some rate of mass n, right? So I'm going to use the superimposed dot to indicate like a time derivative. So that's the rate of mass coming in. And on the what comes out is, well, it has to equal what went in, right? Plus the change with respect to x. So x is in this direction. It's just a one-dimensional media. So the change of mass times dx, right? So the change in mass with respect to a small distance dx times dx, right? And I don't want to confuse you, but you could imagine like if I know the flow rate everywhere, say the mass rate as a function of x looks like some curve, right? If I measure it here and it's m dot 1, and I measure it a small distance away, say dx, then just through a linear interpolation, I have m dot 1 plus, right? It's just an equation of a line. And for over an infinitesimally small distance, the slope is dm dot 1 dx. So that's the slope times the distance, right? So it's just the equation of a line. Right. That's how I get this term over here. Now, that's the mass going out, and we have this minus sign there, right? Generation and consumption, so this is our well. We're going to use the symbol m tilde for that. So that's some infinitesimally small source of injection or sink produced in there, okay? So let's start to write these terms in the equation. So the rate of mass m is m dot, and actually m dot is equal to the density times the velocity. And so, m dot is like the mass, it's a flux, right? So it's like the mass per length squared over time, right? And density, right? Density is mass per length cubed. Velocity is length per time, right? So m is mass, L is length. So density is mass per unit volume, length cubed, right? So then if I cancel these guys, then I have a squared there, and this checks out, right? So the units work. So mass is the density of the fluid times the velocity it's traveling. Okay, so that's m dot. Okay, so the rate of mass n is the density times the velocity. That's the flux. But I need mass, right? So then I have the area times dx, right? So mass is density times volume. I have a one-dimensional media, so it has an area, cross-sectional area here, and a width dx. So the volume of this is a dx, right? So density times volume gives me mass. Mass times velocity gives me the rate of mass n. Okay? So let me actually use a different color just to be clear. So we have density times area times dx times velocity. So this is mass times velocity, right? Minus, now we want this term, and we're just going to substitute in appropriately. So we have, again, the volume, volume I just want to be precise. The final answer wouldn't be different, but I want to be precise. So plus the rate of generation or consumption. And then the rate of accumulation is just going to be, again, now the rate of accumulation is going to be the density of the fluid times the porosity. So that's the volume of the fluid in there times A dx dt. Right. Well, you can see that those two terms cancel. That I distribute the negative sign. Those two terms cancel. All right. Seems I have an extra dx term there. So those two terms cancel, and then I can cancel these guys on both sides of the equations. The cross-sectional area doesn't change. We're just making that assumption here. That would not be true in general, but we're making the assumption that it doesn't change here. And so then we're left, after we distribute this negative sign, with this equation. Where I just moved some terms around. Namely, I just moved this guy to the other side. The generation consumption term, I moved it to the other side of the equation. So this guy is the mass conservation equation. Or also known as the continuity equation. And so this is in 1D.